And it is my pleasure to introduce Souvik, who will talk about asynchronous cellular automata as randomness enhancer.
Thank you, Najim. Let me share my screen. So, okay. The paper title of the paper is Asynchronous Cellular Automata as a Randomness Enhancer. Me, Souvik, with my friend Sumit Adak, presenting this work. So the initial words is that most of the audience are cellular automata researcher. So cellular automata is a very rich object. So people study cellular automata from different point of view. People study cellular automata from computational point of view for solving computational problems. People study cellular automata from dynamical system point of view, and people try to build technology from cellular automata. So in this particular work, we study the dynamical behavior of asynchronous cellular automata and try to understand some technological aspects from this whole study. And here our problem is problem of generating pseudo-random number generator by studying the dynamical behavior of asynchronous cellular automata. So the problem statement, the problem of generating random PRNG. The brief history, if we start from the initial things, we started from the rule 30, famous rule 30, Wolfram's favorite. So PRNG based on chaotic elementary cellular automata rule 30. Wolfram first studied it, then some iterated hash function based on this Wolfram's rule is explored by Dangard, and later on people studied different uniform, non-uniform versions of elementary cellular automaton and other automaton for studying this capability of generating random number. And keeping in mind mainly two properties. One property is the property of chaos. It says that slightly different initial configuration of a CA produces different sequence of configuration having a little or no correlations. And second one is obviously for finding out large cycle for creating good PRNG. They explore the property of subjective property, and it connects with the reversible CA. In mind and searching for cellular automata rules, and it eventually happened that produces good PRNG. So here we are exploring fully asynchronous updating scheme in our cellular automata, elementary cellular automata, and where a single cell is selected uniformly and randomly for update. But the problem is that when you update our cell, the randomness is not actually internal to the system, because if we update our cellular automata following fully asynchronous zoom, so we have to select one cell randomly. So that randomness comes from outside. So therefore, we think that asynchronous cellular automata is not a random number generator, or we can say that it's a randomness enhancer, because for this internal system randomness for selecting one particular cell, we use some source of randomness, and let's see that if we use some bad randomness generator in the source of this internal randomness, what happens if we evolve my cellular automata system, it can capable to increase the randomness capability of this bad randomness generator in terms of some testing parameters. So that's the target of the study. And here, following the previous works on cellular automata and random number generator, our hypothesis is that we try to understand, identify asynchronous cellular automata with large number of cycles. Here, by what large we mean that 2 to the power n or 2 to the power n minus 1, that size of cycles. And the second property we try to understand is that it's happened that large cycles sometimes create some regularity. Like one of the examples is that maximum length linear feedback shift register. That is a large cycle, but it creates some regularity. So only finding out large cycle CAs is not sufficient, we think. And to avoid this regularity, we explore further the dynamic behavior of this large cycle asynchronous, fully asynchronous elementary cellular automata, and we classify this large cycle system into fully and partially exposed system. And our final hypothesis is that a fully exposed system with large cycle are expected to be a good randomness enhancer. So let's see what happened so with this primary to target, this large cycle and this exposed property. Let me introduce the exposed property later. So the basic preliminary is that here we consider one-dimensional 3-neighborhood 2-state cellular automata, elementary cellular automata, and we use a few properties of this or notions of this cellular automata. One is rule mean term, that is we use this RMT for identifying the properties of different elementary cellular automata rules. We also use the property of active and passive RMT. If this remain unchanged, then it will be passive. If, for this case, it is passive, 0 remains unchanged. And if it is changed, 1 becomes 0, then it is active. So this property, and also we invest a few of the properties of primary RMT set. There are these 6 primary RMT sets from this set of RMTs, and any configuration is created by constructing these primary RMT sets, and the equivalent homogeneous configuration of these primary RMT sets are this. So this is the basic preliminaries, and our update scheme is a single cell is selected uniformly at random for update. So this is fully asynchronous cellular automata and elementary cellular automata. So let's move on. So we're trying to find out asynchronous cellular automata are expected to be good randomness enhancer with large cycle size, which is 2 to the power n and 2 to the power n minus 1, and we identify recurrent ACAs of size of communication class is 2 to the power n and 2 to the power n minus 1, and we also identify some ACAs with multi-length attractor where the size of the attractor length is 2 to the power n minus 1. So these two are in terms of this finding out large cycles ACAs. So next, this is one already established theorem by Professor Fates, Sheikh Vishwanath Sethi and Shubhanta Das. They have identified the recurrent ACAs. Recurrent ACAs means if we evolve the system starting from initial configuration, it is possible. It is with probability almost we can almost surely come back to my that initial configuration. So kind of reversibility you can also say, but they named this as recurrent CA in a similar fashion. So this is a established theorem, and they have identified these rules, 18 rules, minimal representative rules, those who are recurrent. And they have also identified the number of communication classes and the size of the communication class. And there are many categories of this number of communication class. 3 are associated with one single communication class. That means the length of the cycle is 2 to the power n. So these are our topic of interest. So out of these 18 rules, there are 6 recurrent ACAs which are associated with one single communication class and length of 2 to the power n. So for our target for generating good randomness enhancer, these red rules are one of our point of interest. And also there are 5 recurrent ACAs which are associated with 2 communication classes. One is of length of 2 to the power n minus 1. That means the length of the cycle is 2 to the power n minus 1 and 1 with only all 0 configuration. So if we don't start with all 0 configuration, in case of generating our randomness enhancer, then these 5 recurrent ACA rules also are point of interest. So from here we get 6 plus 5, 11 rules, which are supposed to be good randomness enhancers because they are associated with large cycle lengths. So this is our first rules. Next, we have identified few rules. Those are not recurrent, but that produces multi-length attractor of length of 2 to the power n minus 1. And here we propose one theorem that a rule R of n cells converges to a multi-length attractor of length 2 to the power n minus 1 with all possible configuration except all 1. That means all 1 configuration is not included in this multi-length 2 to the power n minus 1 cycle. And the condition for identifying these rules are if RMT5 is passive and RMT 0 through 7 are active, and at least one RMT from both of the RMT. And the proof is very simple. First of all, I have mentioned that this all-one configuration is not included within the cycle. So therefore, we have to restrict the journey of other configurations towards all-one configuration. And that point of for that cases, for primary RMT 7, primary RMT 5 is responsible for that journey, and primary RMT active RMT 7 is responsible for the reverse journey. So the first condition is therefore active RMT 7 and passive RMT 5 are the condition for make it not recurrent, but this all one configuration apart from this multi-link cycle. And for rest of the configuration space, we just work with this primary RMT set because all the configurations are created by primary RMT sets, and we try to understand that which RMT is responsible for journey from one primary RMT set to another primary RMT set, and following this we get this result that active RMT 02 and at least one active RMT from 14 and 36 should be active for open this all journey from different RMT sets. So according to this theorem, we get 5 ACA rules: rule 3, 11, 19, 25, and 27. These are associated with cycle length of 2 to the power n minus 1. So next, we are achieving our first target, that we want to understand which ACAs are associated with large length cycles. So next, so therefore we are now with 16 ACAs which are associated with large size cycles. So these are our potential candidates for randomness enhancer. But I have mentioned that large cycle length of a system sometimes induces some regularity. So therefore, we have tried to identify a way to check that the dynamical behavior of these ACA rules. And to do so, we follow some quantitative and qualitative experimental approach. We just evolve the system starting from a random initial configuration over a few time steps, few means large here, and store the predecessor successor relationship during the evolution, and we plot the predecessor successor relationship as a graph where the configurations are the nodes of the graph, and this is the qualitative behavior. And for the quantitative understanding of these graphs perfectly, we evolve the system here for n into where n is the size of the CA and the length of the corresponding cycle. So multiply these two things for give reasonable fair chance to every configuration. We evolve the system for that time step, and we calculate the relative frequency of every configurations of the cycles, and this is the formula for calculating, the simple formula for calculating this relative frequency, which stands for, this is the absolute frequency, and here we follow that time, that number of time steps. So we just divided them and get the relative frequency, and we define that a cycle is said to be fully exposed where for every configuration, for any two configuration of this cycle, if the relative frequency is almost same with some measuring, then we call them as fully exposed, and if they are differ largely, we then call them as partially exposed. And so let us show the result of this experimental approach, and this is rule 33, which we call partially exposed, and this is rule 51, where every configurations are almost equally exposed. You can say if you evolve the system, then they are equally exposed, and here it is hard to reach few configuration. We name this configuration as hidden configuration in some of our other works, and so now observe that this fully exposed system, we can intuitively understand that this system is good for random number generator, or for this work for randomness enhancer. And this partially exposed system, these configurations, it's very hard to reach this configuration, and this partially exposed system may be a good application for cryptosystem generation. Okay, so this is the graph. You can see the relative frequency is almost same for every configuration here, and for this fully exposed system, this is the red line for fully exposed system, rule 51, and this is for 33. This is factoring different configurations with high chance of reach, different with very low chance to reach. So depending on this result, we classify this our 16 rules which large cycle into two classes. One is fully exposed and one is partially exposed, and there are 6 rules: 43, 46, 51, 54, 57, and 60. These are the fully or with fully exposed behavior. And so now our candidate are these 6 rules which are associated with large number of cycles and also with source fully exposed behavior, and these are expected to be a good randomness enhancer. So now back to the technological purpose. Here we use some for this randomness enhancing things. We use some standard technique. We use diehard for our test base, which are 15 tests, and also we need to select a PRNG with 4 randomness quality, because in fully asynchronous C, I have mentioned that we have to select one cell randomly. So for this internal randomness, we have to select one random number generator, and let us see the improvement in that random number generator out of my fully asynchronous system. So we have used rand for creating the randomly selection of the cell, and here we use CSI of 24 to 29, and 1000 initial configuration are considered. And for this diehard test, for each such run, a .bin file of size 10 to 12 MB is generated using the whole configuration of the CA and is given to the diehard. Now let me show the result. So these are the result of these 16 rules which I have mentioned, and the 6 rules with fully exposed behavior are in red. These 6 rules which I have claimed they may be good source of randomness enhancer from my study, and these are the rest. Blacks are the rest rules which are not with this fully exposed behavior. They are with large cycle but partially exposed behavior, and we can clearly see the differences that these rules are showing better results. And but unfortunately, ACA 46 and 60 are not showing that much good result what we have expected. But the rest of the rules 43, 51, 54, 57, they are showing good results for die-hard. So now next we compare our results, and RAND passes one test in case of different seeds for this die-hard. But now my ACA can enhance, because as an input we give RAND for selecting cell in fully asynchronous CA. So RAND is my input source, and what I'm enhancing, so RAND passes one test, and now this ACA with fully exposed behavior and large number of cycles, there passes 8 to 10 tests. So there are comparison with other random number generator also, but the important point for this study is not comparing with other randomness generator. Here we try to compare with RAND, because it's showing that the capability of asynchronous CA for enhancing the power of this RAND as an input. So that's the results, and so for concluding this, I should say that I have further explored why ACA 46 and 60 are not showing, because these two are also with this fully exposed behavior, why they are not showing good results. And also this classification fully exposed and partially exposed we have done purely experimentally. So there is a scope of understanding in terms of RMT, so why they are fully exposed and partially exposed. And we have already considered cycle length 2 to the power n and 2 to the power n minus 1. So if the cycle length is greater than n by 2 and less than 2 to the power n minus 1, so we have to identify those ACA and how they work for this randomness enhancer. And here for input we only use RAND, but if we use other random number generator as an input, and in future we should test that the enhancement by ACA for the other random number generator as an input. So these are the some future direction of this work, and I want to acknowledge Professor Sugant Das and Najim for discussion with this multi-length attractor CS, and Kamanika Bhattacharya for the discussion with this randomness on. And I also acknowledge the whole Cellular Automata India group for my collective understanding on this Cellular Automata and randomness. And so you can open the dialogue and you can ask me questions.
So thank you very much for this nice talk, Souvik. Time for questions now. So if there are no questions, I will ask the first question. I was surprised, Souvik, that you present Rule 51, say, as a good rule, because, you know, Rule 51 is in some sense not a cellular automaton, because you don't take into account your left neighbor and your right neighbor. You just change your state without taking into account the left neighbor and right neighbor. So how would you interpret this?
Yes, Rule 51 is kind of useless. But what happened is that in case of this, because here practically Rule 51 enhancing the capability of RAND, you can see that. And the dynamical behavior also suggests, if we see kind of an alternative approach to draw the basin of attractor dynamics. So I can say that this is the basin of attractor dynamics of Rule 51, where all the configurations are some equal probability to come. So that is the reality. But if you ask me theoretically what is behind this, one thing I can say that this participation of RMT 14 and 36 equally in the RMT sets, maybe one reason behind this enhancing power of Rule 51 for this particular case.
Okay. Are there other questions?
Yes, I have one query.
Yes, please.
Yes, Souvik, you were telling that it's this asynchronous CS can work as randomness enhancer. So you have taken a very bad rule, Rule 30, which if you see the rank, it is almost the lowest rank holder, and you try to improve it using your ACA. Now, my query is if you take the for this external random input or random number generator that you have been using, if you take say machine twister or any very good random number generator, can your ACA make it very much non-random?
So that is exactly what is our future target for extending this work, because we have already explored with random. We have not explored with other randomness generator as a source of randomness in the ACA. So this is our plan of future work. So currently it's not possible to say how it works without experimental study. So that's.
Thank you.
I have see Souvik.
Yes.
You were saying talking about randomness enhancer. See the rank you have shown. I don't know whether you have taken same numbers. Rand is generating some numbers. Have you used the same numbers when you are testing? You are testing, we say a rule in ACA, with ACA. Have you used same number generated by rand for the testing for rand and testing for say some ACA?
No. That's also right. I say because that will be interesting to see the actual enhancing capability. But we are expecting that that does not differentiate that much, but that can be a good extension of this study, because we can play uh, with different random number generator as a source of input, and also by following the same things. Thank you very much. We have not explored in that way.
Yeah. Otherwise, how it is? It is enhancing, or it is enhancing at all? That is not very clear.
Yes.
And you are talking about the recurrent ACAs having the length to the power n or to the power -1, something like that. Is it good that after that amount of time, that amount of expected time, I can come back to the initial condition? There is one way, but if we talk about enhancement, is it the necessary condition that we always need to follow that one? Suppose my is say to the power less than to the power n say, say to the power n-1. Half of the configurations they are forming a single in a communication class, right? And can't it be happen? Can't it happen that that kind of ACA is acting as good enhancer than the other having the larger communication class?
Yes, that's a huge possibility for that, because I have already mentioned that large cycle produces some regularity. That's we know all about that fact. So I think it may be possible that if we work with cycle length of n/2, then it may produce some good result. We have to identify with ACAs with that cycle length or within a range of that cycle length. So it may be possible to identify and work with these ACAs.
Okay. Thank you.
Good. Are there other questions, remarks? No questions? Okay, so thank you very much again, Souvik, and thank you to all the speakers of the sessions, and thank you to all persons attending. So I will ask maybe Sukanta for closing